In this podcast, we are going to explain how to use Valgrind to identify the memory leaks in a given program. What is Valgrind? Valgrind is a multi-purpose, general public licensed programming tool which is used for memory debugging, memory leak detection, and profiling. Now let's have a look at the architecture of Valgrind. Valgrind has a modular architecture. It starts at the kernel, which performs program execution simulation and analyzes the transfer of control and memory management between various modules in the architecture in the program. Valgrind, during the process of simulation, collects all memory related information from the kernel that would help to perform and suggest efficient memory management and to detect the memory leaks. Now, since Valgrind is a modularized in architecture, it has different modules. Now let's have a look at the modules. Memcheck. Memcheck does the primary job of memory leak detection in memory related operations like memcopy and memmove. Cache grind. Cache grind analyzes the execution of code during the simulation. During this step, Valgrind collects all possible memory related data. Call grind. Call grind monitors function calls and memory management, that is, freeing allocated memory, etc. during a function call. Massive. Massive analyzes the memory utilization across the program. Hellgrind. Hellgrind works with threads and sockets. Now let's have a look at the kinds of leaks that can be identified using Valgrind. Checking the validity of memory that is being accessed. To check if an uninitialized memory is accessed. Report access of memory that was freed. Report access of memory blocks beyond allocation made for a particular code. Check if stack and heap is accessed appropriately. Report if we are trying to free memory that was lost or unallocated memory. Report mismatched use of malloc, new versus free, and delete. Report overlapping memory areas in memmove and memcopy and other memory intensive operations. Inefficient thread and socket programming, that is, exchange of data over corrupt or closed sockets. Help us perform profiling. Helps us in synchronizing errors in multi-threaded program. Useful in analyzing memory consumption and suggests efficient memory management. In this project, we are working on the open source code GCC. So it's appropriate that we have a look at what GCC is. GCC is a GNU compiler collection. GCC is a powerful compiler used to compile collection of programming compilers including C, C++, Objective-C, Fortran, Java, and ADA. Once installed, any of the programs from the above list can be compiled using GCC, the program name followed by -o and the executable in which we want the binary to be created. So, what was learned about this tool from doing this project? We got an idea of how memory leak identification is done, how Valgrind is intuitive and easy to learn, and how easy it is to execute. Valgrind identifies memory related issues in both static and dynamic memory allocations. It does not report false positives, and the results it provides are accurate. In this section, we are going to have a look at the memcheck options that are provided by Valgrind and the different modes in which these options can be used. The first option that we are going to look at is the leak check option. It can be operated in 4 modes. They are no, summary, yes, and full. When the leak check is set as no, we get only the heap allocation results. When the option is set as summary, it says how many leaks are occurred in the program. The leak summary can be classified into definitely lost, indirectly lost, possibly lost, still reachable, and suppressed losses. If the option is set as either full or yes, it gives details of each individual leak in the program. The next option is show possibly lost. It can be used in 2 different modes, yes or no. When this option is disabled, the memory leak detector will not show the possibly lost blocks. The next option is leak resolution. It can be used in 3 modes, low, medium, and high. The main purpose of having this option is to see how willing memcheck is to consider different backtraces to be the same for the purposes of merging multiple leaks into a single leak report. When the option is set as low, only 2 entries need matches. When the option is set as medium, 4 entries have to match. And when the option is set as high, all entries need to match. Hence, for serious debugging, we should use the option high, and this is the default. The next option that we are going to see is show reachable. It can be used in two different modes, yes or no. When this option is disabled, the memory leak detector only shows the definitely lost and possibly lost blocks. When it is enabled, the leak detector also shows the reachable and indirectly lost blocks. The next option is undefined value errors. It can be used in two different modes, yes or no. It controls if memcheck reports the uses of the undefined value errors. If we don't want to see these errors, we can disable this option. The next option that we are going to see is track origins. It can be operated in two different modes, yes or no. The main use of this option is to control whether memcheck tracks the origin of uninitialized values. By default, it does not track. That means that it can say that there is an uninitialized value being used, but it cannot say where it came from. If we set this option as yes, memcheck keeps track of the origins of all uninitialized values. Then, when an uninitialized value error is reported, memcheck will try to show the origin of the value. An origin can be one of the following places: a heap block, a stack allocation, a client request, or a miscellaneous source, such as a call to break. For uninitialized values originating from the heap blocks, memcheck shows where the blocks were allocated. For uninitialized values originating from a stack, memcheck says which function allocated the value, but it does not provide any more details. We have some performance issues of using this option. Origin tracking is really expensive and it divides the speed by a factor of 2, and it consumes a lot of memory of the order of 100 megabytes. The accuracy of memcheck, however, is really good, and we should be careful in not using the options track origins equals s and undefined value. Some of the other options which Valgrind memcheck provides are partial loads OK, free list volume, free list big blocks, workaround for GCC, ignore ranges, malloc fill, and free fill. We have a very detailed explanation of all these options in the man page of Valgrind. Value errors equals no because it doesn't. In this section, we will discuss our observations of running Valgrind against GCC source code. Before we move on, let's take a brief moment to think, why do we need Valgrind as the primary tool to identify the memory leaks? The main advantage of using Valgrind is that it does not require the source code files to identify the memory leaks. That is, it works just with the executable. Hence, it supports security integration for the business domains which cannot expose their source code. As a result of these advantages, companies can outsource their memory leak identifications by providing just the executable to the contractors. Now, for Valgrind to work against a source code, we need to obviously have Valgrind installed on the PC. So how do we install Valgrind? Valgrind can be installed by going into the Valgrind's website and downloading the latest setup that is available. The installation instructions are available along with the setup, and it should be a pretty easy one. If we are using a Linux distribution, Valgrind can be installed by providing in the command sudo apt-get followed by Valgrind, and this should install Valgrind on the system. Now that we have Valgrind installed, we need to have an open source project which should be ready and compiled for Valgrind to identify the memory leaks. In our case, we are working with GCC and we need to have the GCC's executable. For this purpose, we go to GCC's website and download the latest source code files and create an executable. In the last section, we saw the different options which Valgrind provides to identify the memory leaks. In this section, we will perform Valgrind's full leak check option to identify all possible memory leaks. So, let's start the procedure. We give the command Valgrind leak check equals full followed by the executable, and in this case GCC. So how does Valgrind perform the leak checks? It traverses through the object file starting from the root to all the interlinked files. It provides us with a descriptive heap summary and leak summary. In the heap summary, Valgrind lists all dynamic memory operations performed in the source code. Heap summary gives us how many bytes and blocks of memory was used in the heap by the program. When we executed GCC against Valgrind, we got the following results. GCC uses 17,211 bytes in 47 blocks. It also specifies how many blocks were allocated and how many were freed after the program got terminated. For GCC, a total of 160 memory blocks were allocated and only 113 were freed, in a total of 29,371 bytes which were allocated. It also performs a search of all the pointers, the not freed blocks, to suggest where to free the allocated memory efficiently. In GCC, it performs search for pointers to 47 not freed blocks. Valgrind also gives a clear, descriptive leak summary stating all the possible static memory losses, and it also suggests certainty in memory loss like definitely lost blocks, indirectly lost blocks, possibly lost, still reachable blocks, and suppressed losses. For GCC, Valgrind shows the following results: 434 bytes in 9 blocks of definite memory loss, 0 bytes of indirect and possible memory loss, a static possible reachable loss of 38 blocks, and 0 suppressed losses. So, what are the inferences we have from executing Valgrind on GCC? GCC is very well formed in static memory management. That is, it does not have major memory losses in the variables that are allocated in the stack, but it does seem to have some issues in its heap allocations. But the heap summary clearly shows that 47 memory blocks were not freed. This clearly indicates that there is a substantial amount of memory loss, and a more scary inference is that 48 blocks are not searchable or reachable by Valgrind, which is a potential threat to efficient memory management.